Okay, so we're back. Now we're on the dot cam. So before we finish up 5.5, just kind of a quick run through of the greatest hits of Chapter 5 thus far. So if you want to be following along, this will be 5.5 concluded. And how's that on the blurriness? Let's see if we can focus that a little bit better. Maybe zoom in a little bit more. I'll have to make do. Okay. So just by way of review, kind of the big things we need to have fresh in our minds. We started out by looking at the natural log and the exponential function of the natural number. And the kind of important stuff from that is that the derivative of the natural log of some function u is going to be 1 over that function times the derivative of that function, which on the flip side led to the integral of this guy is going to be the ln of that function u. So if we want to integrate 1 over u, which remember that was kind of a big deal because previous to the introduction of the derivative of the natural log, we were at a loss for how to differentiate this because we didn't have the power rule to save us there, because u to the negative 1 led us to an issue. And so this integral turns into the ln of u plus some arbitrary constant c. And so those are our natural log formulas, which then led us to an exploration of the natural exponential function, the e to the x function. And we stumbled upon this incredible fact that the derivative with respect to x of e raised to some function u of x, incredibly, is itself. Of course, with some chain rule in there, e to the u times the derivative of u. And then, in a similar fashion, from this derivative we can get to the integral for the natural exponential function, namely that the integral of e to the u du is equal to e to the u plus c. Okay, and we had a fair bit of practice with integrals and derivatives, dealing with the natural log and the natural exponential function. But what we had started to do in 5.5 was to expand that outside of just the natural number e, and look at other exponential and logarithmic functions. Okay, and so that's what we're going to conclude with today. We had started to look at the derivative of the exponential function of any base, and now we're going to see what about the logarithmic of any natural function? Sorry, of any a logarithm of any base. So one last kind of thing of review that's going to pop its head up today is that we had this kind of interesting definition of an exponential function of base a. If you remember from our exploration of 5.4 earlier, or it might have been 5.4, whatever it was, we said that because we can write this expression e raised to the power of ln of whatever, because of the inverse nature of e and the natural log, this expression is going to be the whatever. Okay, so whatever we put in these parentheses, those two things are equivalent because of this inverse nature of e and natural log and the fact that they kind of like cancel out. Mr. Smith had done a pretty poor job of trying to conceptually explain why that's true. So for now, in our distance learning state, we're going to stick with this kind of canceling out nature of those two things. I bring this up because if we stick in the exponential function of some arbitrary base a, like a to the x, as our something, and we can see that a to the x is the same as e raised to the ln of a to the x. And I believe the book even went one step further, bringing this x down. And so we have this definition of the exponential function of any base is equal to e raised to the x times the ln of that base. And from there we got the definition of the derivative of a to the x by differentiating the right side and using what we knew about the, oh, I'm sorry, that's a typo. Should be an a in here. Told you we were doing this live. By differentiating the right side, we got the derivative of the exponential function of any base, namely that derivative of a to the x with respect to x will be equal to, I'm sorry, let's make this some function u of x. It's going to be equal to a to the u times ln of a times the derivative with respect to x of u. Okay. And that's all well and good, and hopefully somewhere in your brains from previous lectures. We did some examples with that. Oh, and then I guess we should go back. One last piece of review, that the opposite direction, the integral of a to the u du turns out to be a to the u divided by ln of a plus c. Okay, and that's all fun and great and wonderful. And so we're going to do the final piece of this puzzle, which is, what about not the exponential function of an arbitrary base, but the logarithmic function of an arbitrary base? What does the derivative and integral of that guy look like? No? Well, let's find out. So, first, the definition. Definition of the logarithmic function. To the base a. And the definition we're going to go with is that y equals log base a of x if and only if a to the y equals x. This tells us growth. This tells us how long. What is the exponent? What is the time it takes to get to this growth? Okay. And the same properties of logarithms that apply to our natural log, of course, apply to our regular arbitrary base log. Multiplication turns to addition, division turns to subtraction, etc., etc. Okay. At this point, it's also worth mentioning this idea of changing the base of a logarithm, which, of course, comes from the fact that when this textbook was written, and when most textbooks were written, most calculators available to students did not have a log base a of x key. I know that is almost universally not true anymore for your guys' fancy calculators, but because it used to be, we have a way to turn any logarithm into a quotient of the natural log. Okay, what do I mean by that? I mean that if we start from this definition, that y equals log base a of x, and flip to this definition of it, that this means by definition that a to the y equals x. If we hit both sides of this with a natural log, maybe change colors here, yeah, that'll be fun. So everything is about to get linned. That allows us to say that y times the ln of a is equal to the ln of x, where the left side of this comes from dropping down that exponent, and then dividing both sides by the ln of a, we have that y equals the natural log of x divided by the natural log of a, and then resubstituting in this definition of y, we have that the log base a of x is exactly the same as the natural log of x over the natural log of a, which you have seen previously as the change of base formula. Which is a useful thing not only if your calculator does not have this button, but is also from where we will derive the derivative of the logarithmic function from this definition. Okay. So take a moment, convince yourself that this is true, and then we'll see how this leads us to the derivative for natural log. I'm going to do something now that seems a little bit random, but it will make some sort of sense in a minute. That if we use the change of base formula, where our argument is e, so for example, if we look at log base a of e, our change of base formula tells us that this should be equal to the ln of e divided by the ln of a, but then of course the natural log of e is just 1, so this is 1 over the ln of a. And so we can define log base a of the natural number as 1 over the ln of a. Okay, cool. So we're going to determine the derivative of the log of any base by differentiating this guy. So let's do that. The derivative with respect to x of log base a of x will be the same as the derivative with respect to x of the log of x, sorry, the ln of x, I already screwed this up, over the ln of a. Okay, well, let's consider this right side for a second. A is just some real number. The ln of a is also just some real number, and so it has no effect on the derivative with respect to x of this function here. And so we can write this as 1 over the ln of a times the derivative with respect to x of ln of x. Okay, this is the same exact thing as just kind of pulling a constant out in front of a derivative. 1 over ln of a is just a number. Okay? So really we're just taking the derivative of the ln of x, which we know is just 1 over x. So this derivative starts to look like 1 over the ln of a times 1 over x. And now this little rigmarole we did up here is going to come into play because we just convinced ourselves that this guy is the same as that guy, and so we can write this derivative the log base a of x as the log base a of e divided by x. Well, cool. Which leads us to the theorem version, where we're going to replace x by some function of x that we will call u. And this is the 5.5.5 theorem. That is satisfying 5.5.5. Yes, I think so. Which says that if u is a differentiable function of x, then the derivative with respect to x of log base a of that function u is exactly equal to the log base a of e divided by u times the derivative of u. Or, the first part is only true if and only if we can also replace log base a of e with this definition, which leads to a derivative that looks like the following. 1 over ln of a times u, put some parentheses in there, times the derivative of u. Well, cool. Okay. So now would be maybe a good time to take a quick break if you need to. It's been about 20 minutes. There we go. Stretch your legs a little bit before we get into the examples, of which there are a few. We're going to do 4. So I'm going to press pause here, make sure that this is actually recorded.